Vincent?
Hi everyone. So I'm going to speak also about the lovely pyramid wavefront sensor non-linearities. Okay, and the way we deal with it at LAM with a focal plane assisted method. Okay, so let's go. So just to sum up the optical gains, but actually we spoke a lot about it today. The optical gains, it's an offset between the calibration and the on-sky regime of the pyramid. So usually a typical optical gain curve looks like this for a modal basis. So here I use a KL mode. Okay, so for example, for one given mode, if you calibrate with a point source calibration, if you send one, you will get one. And once you're on sky, actually, because you have residual phases and you're not in a perfect correction regime, you will, if you're trying to send one of this mode, you're going to measure something less than one. And so you have a loss of sensitivity, which is frequency dependent. So that's the thing with optical gains. Actually, it's due to the pyramid non-linearities. So handling pyramid non-linearities, it's mainly trying to keep track of the optical gains, these famous optical gains. Okay, and so it has a lot of application. So it helps for the bootstrap to have this value of the optical gains for predictive control, PSF reconstruction, and also for NCPA as we saw before. Okay, so what we propose at LAM is to use a focal plane assisted method. So what it is, actually, we propose to put before the pyramid what we call a gain scheduling camera. So it's a camera which is going to take a short exposure of the PSF on the tip of the pyramid. So of course the PSF is modulated, and then we see that what we get on this camera is a PSF convolved with the modulation circle. And once we have this data, actually we can use the convolutive model. So Charlotte Bond explained the convolutive model before. So actually this model is allowing us to compute the impulse response of the system. And so with this data from the modulation camera, the gain scheduling camera, we can deduce the impulse response of the pyramid, and therefore we can deduce its working point, let's say. So actually, okay, I'm doing a quote from today from Enrico Pina, who said that, okay, yeah, the hard thing with the optical gain is to try to track them quite fast, and also to have a robust method for when the seeing is changing a lot. And actually, this method we propose is a way to really track really fast, in a fast manner, the optical gains, and which is really robust to the change of seeing conditions. So actually, one way to demonstrate the efficiency of this method is to work on the NCPA. So you saw that it's a really, a really important case for the optical gains, because actually focusing on the NCPA is important, because we know that if we manage to correct well the NCPA, that means we have the right optical gains on the pyramid. So okay, the NCPA, you know all what it is. So if you have to have a flat wavefront on the science path, you need to put an offset on the pyramid. And so the PSF you want to have on the tip of the pyramid, let's say, should look like not a diffraction limited PSF, but something with the NCPA on it. So you have to offset, you have to put offset on the pyramid. So the offset reference on this pyramid. And these offsets, as it was said before in the previous presentation, they have to be scaled with by the optical gains. It's really important. So actually, if we close a loop, okay, on the system, it's okay. I took a 8-meter telescope with a classical AO system. Let's say if we try to close the loop and then we try to inject NCPA, what can happen? So either you're going to converge towards a wrong value of the NCPA, or even worse, you can make the loop diverge in some condition, especially if you have quite strong NCPA and also if you have a strong seeing. You can make the loop diverge. It's what I call the NCPA catastrophe. Why? Because you're going to put an offset reference on the pyramid without taking care of the optical gain. If you do that, you're going to push too much, as Enrico Pina showed in his previous presentation. But if you're pushing too much, you can create, more optical gains that will make you push even more, and so on. And so you can make the loop diverge, and it's of course a big problem. So okay, we know that to solve this problem, we have to take into account the optical gain in the computation of the reference map of the pyramid. So if we do that, okay, so with our modulation camera, what we can do is actually we compute without the NCPI. Before the NCPI injection, we compute the overall optical gain, and then we multiply our reference by this optical gain, and we manage to stabilize the loop. But actually, with this solution, with this gain scaling camera, what we can try to do is even more than that, is trying to, at each frame, to keep track of the optical gain. So at each frame, we take a short exposure image with the gain scaling camera, and we put that in the convolutive model, and we compute the optical gains. So we can have a fast tracking of these optical gains. And so it's a method which is robust with seeing changes and stuff like this. So in this simulation, the seeing is stable already, but I mean we can we will have even more gain if we make the R naught change. So this is our solution for the optical gain. Of course, the correction is not perfect, because we should reach. If we are correcting the NCPA in a perfect manner, we will reach this average on the straight ratio. Actually, we have this difference because when we do this optical gain stuff that we are all of us are using this approach. We are assuming that the pyramid has a linear response, which is kind of changing at each frame, but we are still focusing on a linear response, and we are still working with matrices. So this is the first approximation. The other one is that we use the diagonal approximation. And then for us, because also we have this convolutional model, convolutive model, which also makes some approximation that make the difference between this step between these two parts of the plot. Okay, so this is our solution. It's working well in simulation, but something that we have to think about is that there is a big drawback on this solution, is that we still photon on the way, and so of course that's a problem. In AO we don't want to lose any photons, right? But actually we did some simulation to try to see what is the impact of the photon noise on our data when we take this gain scaling camera. So we play with this data from the gain scaling camera by putting more and more photon noise on the data given by this camera. And actually, so here on this plot, we have curve of the optical gain. So the blue one is end-to-end simulation, and the red one is the one given by our model with the input as which is the gain scaling camera image. And so we saw that if we take 10% of the flux for a given magnitude, so here it's 5 in the visible, actually we don't have an impact on our estimation of the optical gain. If we go to 1% of the flux, if we steal 1% of the flux, we still don't have almost no impact on our measurements. And we can even go lower than that. So after we see that the low modes, the low order modes can start to be impacted. But still, we see through this demonstration that our method is really robust to the photon noise. So this corresponds also to a fainter star with a 10% flux, which is stolen by this solution. Okay, so I don't have so much time left. So the goal is to do some tests on Loop's bench. Of course, the COVID was slow us down. But okay, so on the Loop's bench, what we have is a SLM, so a spatial light modulator, which is in the pupil plane. So we can really simulate high order aberration in the pupil plane. And also we have another SLM in the focal plane, which allows us to make a lot of different shape of mask. So we can play with this high order aberration. We can also do pupil masking with a central obturation, or we can add spider on the pupils. So with all these elements, we can try to test a lot of different configuration, AO configuration, to try to probe our solution to see if it's working. So we installed this gain scaling camera on the Loop's bench. So here is the unmodulated PSF, and when we are modulating the PSF, we can see, so here is a fitting limited, just a fitting error PSF. We see that we have this kind of data, which is the data from the gain scaling camera. And so we settled this, and now we are trying we are taking some measurements to probe our solution on the bench, on our IO bench. So stay tuned for the results. And then the next step after this bench test will be to to go on sky. And so we have this project, which is the Papyrus project at OHP. And I mean, Gilo 10 will speak about this much more tomorrow at 4:20. And thank you all.
Thank you, Vincent. I'm not sure we've got a lot of time for questions, but if there are any, you can answer to in the Slack, of course. Okay, thank you very much.